Hey, I'm Mark. I'm an AI resident in Google Zurich, and I'm going to present some recent work we've done on training deep neural network classifiers under input-dependent label noise. So, just starting off with some definitions. So we can subdivide uncertainty in machine learning into two categories. So one is epistemic uncertainty. This is a type of uncertainty that's captured by Bayesian methods or Bayesian neural networks. And that's uncertainty basically about the model that generated the data. But there's another type of uncertainty, which is called aleatoric uncertainty, and this captures inherent noise in the data set. So that could be as a result of noisy measurements, it could be mislabeled examples, it could be that you have missing data or unobserved some of the predictive variables, and so on. And then we can subcategorize aleatoric uncertainty into homoscedastic uncertainty. So this is where basically the aleatoric uncertainty is constant across the input space. For example, maybe every label gets flipped with 20% probability or something like that, versus heteroscedastic aleatoric uncertainty. So this is where basically different examples, different areas of the input space have different levels of aleatoric uncertainty, which maybe some examples are harder to label than others, some are ambiguous, some are not ambiguous, etc. So what we're focused on is on heteroscedastic aleatoric uncertainty in classification. But before we move on to that, I'll just show how to model heteroscedastic uncertainty for a regression model, because it's very nice interpretable and it's easy to understand relative to the classification case. Suppose we want to fit a regression model to a data set. The standard thing to do, right, is to minimize mean squared error, which is basically equivalent to maximizing the log likelihood, where you assume that the variance is known. So fitting the mean parameter of a Gaussian and assuming the variance is known. So if we now assume that basically instead of the variance being known and equal to 1 everywhere in the input space, we have heteroscedastic uncertainty, we want to fit a neural network to predict not only the mean parameter of the Gaussian, but also the variance parameter of the Gaussian. And so that's basically what we're showing here. So we fit the mean parameter with a neural network, fit the variance parameter with a neural network. And then when you write down the log likelihood of this model, it has this really nice interpretable form where you still have these squared error terms for every data point. But each squared error term is weighted inversely and proportional to the predicted variance for that data point. So basically, those data points with high predicted aleatoric uncertainty will be downweighted in the loss function, and those with low predicted uncertainty will be upweighted in the loss function. And that basically results in less overfitting to noisy labels, which improves generalization. And that's why these methods tend to work. So we want to do something similar to the regression case for classification. And the way we're going to do that is we're going to assume a slightly different generative process for the way our labels come about in a classification data set. So actually, when you fit a softmax cross-entropy neural network on a data set, you're actually assuming something like this generative process. So what you're assuming is that there's a latent variable, and that latent variable has some observed reference utility, f, which is a function of the inputs, and has some unobserved stochastic component, epsilon. Now, if you're fitting a softmax cross-entropy model, this epsilon parameter is considered to be distributed Gumbel 0,1, and the probability of a particular class being picked is the softmax. But we want the uncertainty over the labels to vary across input space. So we're going to put a different distribution on epsilon here. And we're going to assume that distribution is Gaussian with zero mean, because we can incorporate any difference in the mean into this reference utility, and some unknown variance, which we're going to fit a neural network on. And then we're going to assume that the probability of a particular class being selected for the data point is the probability of this latent variable being maximum over all classes. So the probability of the argmax of that latent variable being C. So that's our assumed generative process. But we run into some problems with fitting a neural network to that assumed generative process. And that's basically because the argmax is non-differentiable. So what we do is something similar to the Gumbel softmax trick or the concrete distribution, where we're going to approximate the argmax with a softmax at some non-zero temperature. So this is just a little derivation showing that we can rewrite the probability of the argmax over the latent variables as being equal to an expectation over a softmax, where in the limit of the temperature of that softmax going to 0, and then we're just going to approximate that expectation by setting the temperature to some non-zero value. So yeah, that's our basic view of how to define the generative process and then approximate it with a softmax for heteroscedastic classification models. And it turns out actually that this view generalizes and explains a couple of methods that already exist in the literature. And these methods in literature, basically what they do is they place a normal distribution over the softmax logits of a standard neural network classification model, and they just implicitly set the temperature to 1. And we're actually basically providing a theoretical framework for the same approach, where we're saying that actually the temperature in those models, which they all set to 1, controls a bias-variance trade-off. So when the temperature is low, the bias relative to the argmax is low, but the gradient variance is high, right? So in the limit of 0 temperature, the gradient variance is infinite. And at high temperatures, the gradient variance is low, which is nice, but the bias relative to the argmax is high. And what we're basically arguing in our work is that you should view heteroscedastic models, classification models, according to this generative process, and that you can actually tune the softmax temperature on a validation set to control that trade-off and therefore control performance as well. And yeah, so basically we have a bunch of experiments that show that our idea essentially works. The first is basically we add some heteroscedastic label noise to standard image classification datasets, so CIFAR10, MNIST, and SVHN. And this table is basically just showing that when we add this label noise to these data sets, we get better log likelihood, we get our accuracy on the test set, and we also get better accuracy on the clean test set, so when there's no label noise added to the labels. And actually, interestingly, if you apply our method to these data sets, so CIFAR10, MNIST, SVHN, even without adding any heteroscedastic label noise, so just the standard data sets, our method actually outperforms standard neural network training and also the other heteroscedastic baselines. So the performance improvements are more marginal than when we add the heteroscedastic label noise, as you'd expect. But actually, it seems like these data sets, which are mostly cleanly labeled, actually have some form of heteroscedastic label noise in them. And yeah, particularly on SVHN, we got a nice little log likelihood and accuracy bump just by using our method relative to standard neural network training, which is nice to see. Yeah, and so then we looked for other data sets that had naturally occurring heteroscedasticity. And so one good example is image segmentation, because basically the pixels around the borders of images are often noisily labeled, just because it's hard to just say whether it's pixels in the background or it's in the object or whatever. So yeah, we applied our method then to PASCAL VOC and Cityscapes, to standard image segmentation datasets, and we also got some nice results. So for instance, here's some example segmentations. So yeah, on the left is an original image. This is actually out of any of the datasets. So this is a model trained on PASCAL VOC and then applied to this image. And we have like a standard image segmentation model, which is trained using the standard Softmax entropy loss. And then we also have the heteroscedastic models that set the temperature to 1, and we have our method, which is the heteroscedastic model, but sets the temperature to, or tunes the temperature on a validation set. And then down here we see some of the uncertainty heat maps for the various classes, and you can see some cool artifacts that basically in or around the pixels at borders you have high uncertainty, and for the rest of the pixels there's very low uncertainty. So basically what we're seeing is our method is overfitting less to these noisy pixels at the borders of images, and as a result we actually get better performance on the test set as measured by mean IOU, which is like a standard metric for image segmentation quality. This is basically showing this trade-off that is controlled by the temperature. So at temperature 1, which is these other heteroscedastic methods, you're actually underperforming the standard homoscedastic softmax entropy training. And when you tune the temperature on a validation set, which is our method, you're outperforming both the heteroscedastic and the homoscedastic baselines and getting quite a nice little performance improvement for both data sets. And this is a table basically showing the same results. So yeah, so basically in conclusion, we argue that you should view the generative process for a heteroscedastic classification model according to this latent variable generative model that we defined earlier, and that the softmax that's used in many of these heteroscedastic classification models should be viewed as an approximation to the argmax in that generative process, and that you should tune the softmax temperature on a validation set to control the bias variance trade-off in that approximation, and that if you do that, you basically get better performance. And that's what we've basically shown in our work.